Hey, good evening, everyone. So today I will be presenting this paper, the multi-user augmented reality with communication efficient and spatially consistent virtual objects. So this is the outline of the paper. So augmented reality application exploded in popularity, and right now there are many multi-user AR being available in many applications. As we can know, there are sort of like Google Cloud Anchor, Just the Line, and Pokemon Go. To the left side is the Google Cloud Anchor. As you can see, it's like they're playing a game, but there's actually a virtual, a augmented reality object there. And Just the Line and Pokemon Go, all these use the AR application, and it can be used in multiple users. An example of a multi-user interactions in AR. So let's say we have two people, which is Alice and Bob, and they both have the smartphone on their right arm. So the first thing is, the first interaction is Alice places a virtual object by tapping the screen. So here, Alice just puts a Spider-Man head in this position. They just put it on the screen. And then we need to render the virtual object. So Bob waits for it to appear on his screen. So like for a moment longer, the object will be shown in the Bob screen. And then the next interaction is the subsequent user interactions. So what Alice can do is that she can tap the screen to move the virtual object or place a new virtual object. And Bob just waits for the update to reflect it on the screen. So as you can see, what Alice can do is that first she can move the Spider-Man to the upper position, or she can place a new object, which is the Iron Man, in the bottom. And then Bob just wastes a bit of time to get the object, the virtual object. So what is the issue for this type of multi-user AR application? First is the communication latency. So as you can see, every time that Alice places something, Bob has to wait for a moment to get the information that Alice provides. And so this is the examples of the communication latency. As you can see, on the left graph, there's the transmission speed and the time. So at the 20-second time mark, that is the first initial visual feature. As for example, like I'll just put the Spider-Man object, and then this sends this information to Bob, and the other two are the user interactions. So these, like, you can see that every time you do something, the resolver has to wait for it. And on the right, there are some applications we mentioned, like Cloud Anchor, Just the Line, Minecraft, Pokemon Go. All these have latency issues within. So this is the issue for communication latency. Next, we talk about spatial inconsistency. Is that even you place a virtual object in different devices, you may view like the object might be in different positions. So as you can see in Alice's view, the virtual object, this green guy, is on just right on top of the laptop. But in Bob's view, you can see the green object is like a bit of way from the laptop. So this is some inconsistency between the users. And another discovery is that if the host and the resolver, the angle is more than 60 degrees, sometimes you will fail to show the object. For example, like if they are more than 60 degrees, and when the host puts an object, then the resolver might not even get the virtual object. So this is the spatial inconsistency issue. So what this paper tries to do is to lower these two issues. And then we will be talking about the SPAR, which is the spatially consistent AR. And we will talk about the overall architecture, which is shown here. So on the left side is the host, which is Alice here. On the right side are resolvers, which are Bobs. Like you can have many Bobs in the world. So right side are all the resolvers. So the host will send do something, and the resolvers are supposed to get some information out of it. So there are four topics we will be talking about in this architecture. The first one is the adaptive AR communication. The second one is the coordinate system alignment. The third one is the updated AR rendering, and the fourth one is spatial consistency and estimation tool. So first thing we'll be talking about is the adaptive AR communications, which is shown right here. To align the positions, the host sends to a resolver a set of keyframes, associated point clouds with those keyframes, and the virtual object's coordinates. So these are the things that you need to send from the host to the resolver. And what is
yes. Before you go further, because this AR and VR things are kind of new to me. So what do you mean by associated point cloud?
Okay, so when the host sends a set of keyframes, so these keyframes are like some informations about an object. So the associated point cloud, it means that these will be like the positions of the keyframes. So if you send a keyframe that which is a point, and the associated point cloud will be shown in like X, Y, Z. So it's like 3, 4, 5 in the position. So if you send a set of keyframes, there are like multiple points.
So the cloud here is kind of similar like groups or something.
Yes,
right?
yes, yes.
It's not means it's cloud computing or whatever.
No. Yeah. Okay. Yeah, the cloud just represents the groups. Yeah, so you can see like, so if someone sends a set of keyframes and you view it from a 3D dimension, you will see that it looks like a bunch of things are crowded together, clutched together like a cloud. Yeah.
So how do you define the frames? Is it similar to what we generally understand frame?
Yeah, these are the you can say these are like camera frames, but they are in like 3D. So if you have a camera, you take a picture, there's a 2D picture, right? There has like X, Y coordinates, and in here they just put in like a 3D. Yeah.
Okay, please continue. Thanks.
Okay.
So here the point cloud looks like the position, but how about the third one, coordinate? I think it's also referred to the position, right? What's the difference of these two?
Okay, so I think that what they talk about is like because the set of keyframes, like not all the keyframes are the virtual objects, right? Like if you send a information, you pretty much send the real world information as well as the virtual one. What they want to talk about is like the virtual objects are the ones we really care about. So that's the way they point it out in this way, is the coordinates. And also the coordinate concept will be used later to have some transformation, that kind of stuff. So yes, coordinates, you can say they are just another way of saying position, but the coordinates of virtual objects means that they have a more important thing to say about, like later on.
So here, do they mean, for example, the keyframe just like some snapshots or say pictures, say in the continuous camera, right? So I just do some snapshots and I take this snapshots. right? So just a few pictures. And associate point cloud with those keyframes is like all the possible. It doesn't matter it's virtual, it's real objects, their coordinates in this snapshot. And the virtual objects coordinates we're talking about, you know, the virtual things we generate, their coordinations. Are they talking about three things like this?
Yes. So
Okay,
yeah, so
okay.
you can say that picture, but they some of those like they won't use like all the keyframes in a sense. Yeah.
Okay, just like a continual video, I just take some snapshots. Those snapshots probably is going to associate with your virtual AR or whatever, right? So
Yes.
something like that. Oh, okay, okay. Well, yeah, because it's a kind of a new thing. So you need to make this language understandable, you know, by all the audience. Yeah. Okay. Okay.
Okay. So we'll be talking now about the adaptive AR communication. So the point is like sending all the keyframes will incur significant communication latency, right? Because if you need to send lump all the message or the information in one, that's gonna take a long time to send it. So that is one of the downsides. So in this paper, they provided like two strategies, like the SPAR small and the SPAR large. And here's a picture that demonstrates this. So how SPAR small this strategy work is that they choose the keyframes that are close to the time when the virtual object is created. So for example, like if a cube is created like at t equals 0 at this point, then they will send those close in. So t equals 0, t equals 1, t equals 2. They will send those that are close to the time when the virtual object is created. As for SPAR large, they send the keyframes that are close to the virtual object. So and those examples like SPAR small and SPAR large, they could apply to the same keyframe. Like you can have a keyframe that is both very close to the time when the virtual object is generated, and also is the keyframe is close to the virtual object itself. And so these are the two strategies, and this is how they choose the keyframes that are more important. And how they determine the importance is the related to the virtual object. So, and by choosing that, they can get the more important information, and less they don't need to send other redundant information. So that's how they lower the communication latency.
Could you go to first one? So SPAR small is send a few frame when the virtual things is close to the virtual things is created, right? That's the SPAR small.
The time, yeah, the time.
The time only relate to time. So SPAR large, you send out like the time around the things created. Why does not include the t equals to 0? It's also the time around the things was created.
I'm sorry, I don't.
So
can you repeat the question?
Yeah, you can check the SPAR large, right? It's the red one, right?
Yes.
The red one contains t equals to 1 to 2, probably to something like this. But for SPAR small, it contains t equal to 0, equals to 1 or something. Why SPAR large does not contain t equal to 0?
This is just so how SPAR large work is that they send the keyframes that are close to the virtual object, right? But so in this case, this is just an example of they just show that T1, T2, and T3, and the other one down there is close to the virtual object. So if the sparse large doesn't choose t equals 0 keyframe in here, that means that the t equals 0 keyframe is not close to the virtual object. So this is just they just demonstrate how it works. It doesn't really mean that much. Yeah.
So sparse small contains everything from the virtual objects created until now, something like that, right? For sparse small, include all the
sparse small create get the keyframes close to the time the virtual object is created. And sparse large, so one is in terms of time, is related to time, and the other one is related to space. That is the difference between sparse small and sparse large.
Okay, okay, that's better explanation. But how can you determine from, because this is you try to determine that from time point of view, right? Example, try to show that from time point of view.
Yes.
I guess probably they use the trajectory information to say, to design the spatial information and choose which frame to be sent in sparse large. Is that the case?
Yeah, they will get the information of what are the keyframes that are close to the virtual object, and that's how they choose them as the those keyframes that can be sent through sparse large.
Okay, so here's the question, right? You call it a sparse large and sparse small, right?
Yes.
Sparse means spatial consistent, and you use the large and small to distinguish them.
Yes.
But according to your explanation, sparse small should be called something like the temporal related, and the sparse large is just like spatial related, spatial
Yes.
consistent, and
Yes.
sparse small is a temporal consistent. Is that the case?
Yes.
Why they use the sparse large and small then? Literally,
Okay.
from English meaning, right? Sparse large in general, based on English words, sparse large should include sparse small. Or see, the sparse small should be a subgroup of sparse large. That's from the English words meaning. But obviously, from the picture, is not in that way. But if according to your explanation, I would say sparse small will be temporal, and sparse large will be spatial. So I try to figure out that where the large and small come from. Yeah.
Okay. So there is a explanation is that the sparse small, they pretty much they work on the when the environment is relatively small, because if you send the keyframes that are close to the time when the object is created, then pretty much when you send it, it's not gonna change that much. So the way they talk about small and large, I think, is that they like sparse small, it is better in a smaller environment, and the sparse large is better in a large environment. So because sparse large is like, if you use sparse large, that means you are sending the keyframes close to the virtual object, right? And let's say if you're in a large environment, doing so will pretty much like filter out the redundant information that are not close to the virtual object.
Okay, so you're saying the small and large, they're talking about a small environment or large environment.
Yes, like, yeah, and in the experiments, they also mentioned like how the sparse small, they pretty much work better in like small environments, and spar large they work in large environments. Yes, like even though the concept, one is time, one is spatial, and the results is how they give their names to it. Yes.
Okay, but do they justify why for small environments, the temporal metric works better than the spatial one, and for the large environment, the spatial one works better than the temporal one? You know what I mean? I mean, if we're according to combination, permutation, whatever you call it, right? In small environment, we should evaluate, you know, temporal one and spatial one, and probably temporal and spatial joint one. In large environment, we need to evaluate these three metrics again. Then we can tell, you know, in which environment, which metric is better. Do they do something similar to this?
They do show that they, like for example, they gave the spar large, like they mentioned about this, like if it in a large environment, if you choose the keyframes that are close to virtual objects, that means you are sending the information that are more important that way. So and this works better in a large environment, because in a large environment there are a lot of things, and there are a lot of places that can be far from the virtual object, right? So if you just choose those that are close to the virtual object, that means you are pretty much limiting the spaces you are sending those keyframes, and doing so you can get a lot better communication latency in the spar large. So that's why spar large works better in a large environment. That is how they gave the explanation. And for spar small, they talk about like if in a small environment, what will really determine is pretty much the time, because in small environment there's really not much places that are going to be far from the virtual object, right? So what they choose to do is to use the time, because in a small environment, those factors, time factors matter more. So that is their explanation for spar small.
For spar small, I can accept your explanation. Say, okay, the environment is small, itself is small. It doesn't matter. You don't need to differentiate, say, from the spatial point of view or from temporal point of view, right? You just send a drawing. You just send everything around that time point. I can accept that because it's itself the size is not that big. But for spar large, I don't think so. For large environment, it's not necessary, at least. Both the spatial things and the temporal things, they change significantly. Say, for example, you do some GTA, this kind of game, right? The environment changes every minute. I mean, every second, or every milliseconds, right? So how can you say, okay, I just send out the things around the things, I assume they're kind of static, not dynamic over time, will be a better solution. Well, I don't know, at least from spar large, you need to jointly consider the temporal and spatial things. That's the things I can accept. Okay. Otherwise, you need to give a certain kind of assumption. Say, okay, for the large environment, stuff are static, you know, not change much. So you only use the spatial information, then probably that's acceptable. But anyway, yeah, I hope when you give this, in particular, this figure is really confusing, honestly.
Okay.
It does not help you to explain what is spar large and what is spar small. I know probably it's a picture from their paper, but still, when you do the presentation, you need to think about that, right? Okay. How can you make the audience never read this paper before we can quickly catch up with you?
Okay.
But anyway, yeah, please move on.
All right, so this is the adapted AR communication. And next we'll be moving on the coordinate system alignment. So the main challenge for the position determination is like each device world coordinate system is initialized at wherever their device is. So like there are two devices, right? So one is set at one is initialized as point A, and the other one is initialized as point B. And because they are in different places, then even if a same object is shown in point C, but they might show different coordinates between the two devices. And devices they launch randomly by users from different locations, as we just mentioned. Like you have different devices being launched at different locations, so that makes the coordinate. You need to make sure the coordinate is well aligned. So the coordinate system alignment for resolver, what it has to do is to transform a virtual object's coordinates from the host to a resolver's world coordinate system. So given this, the one on the left side is the world coordinate system, and the middle one is the device coordinate system. The right one is the world coordinate system for the resolver. So that is how that is the main idea of doing this alignment. So you have to show that you have to show precisely where the virtual object is in the view of the resolver, right? The virtual object. So in this process, the RA and TA, they represent the transformation. You can view it as the pose of those devices, and so you can use it as the pose of the devices. So the way you are using a device, the way you're holding a device, and you create a virtual object, and you will get a the corresponding coordinates from it. So this one, because you are the host, so you are sure about how the transformation is. So in this one, the RATA, they are known parameters. But what is the problem is that when you try to look at the device coordinate system to the coordinate system from the resolver, the difference between the host and the resolver is unknown, because you don't know the relation, the transformation between these two. So what they try to do, what they try to do is they use the PNP, which is the perspective endpoints method. And so in the single user PNP method, only the query keyframe from the device own world coordinate system. But in the multi-users PNP, they query the other the Alice's keyframe instead. So I will be talking about this in the next one. So as you can see, these are we just mentioned the RATA transformation from world coordinate to host device coordinates. So how a PNP usually works is that when you are given the coordinates, for example, like, and you are given x1, y1, z1, and then you are also given the image data of the coordinates. So like in the real world, you take a picture and the virtual object is shown as x1, y1, z1, but in the image, it is shown like mu1, v1. So with these two, with the PNP, you can actually get the pose of the camera, which is shown right here. You can think of that, like if you take a picture of anything, and in the photograph, you will see how it is shown, like where it is shown in the photograph. So, and in reality, you also know where the object really is. So with these two given information, you able to know like, okay, so maybe you are facing, your camera is facing this side and instead of the opposite side. So this is how they get the transformation of it. So this type of transformation is, you can get it, the coordinate relation between the virtual object and the host. So what we have to solve here is the
allow me to ask you a question.
okay.
So from AR things, right? For example, for the host device,
Yes.
what's the difference between the world coordinate and your coordinate? Okay, let me finish my question first. Okay, so from my understanding, right, probably the 0 point change, because I saw the things from my eyes, from my angle, right?
Yes.
The world coordinate probably is standard one. But if I saw the stuff from my angle, then the 0 point change. So everything changing that way. Is that the things what you're talking about?
Yes. So these are 3 coordinates. You can just say that if you're standing at the 0, 0, 0 of those coordinates.
But
so yeah,
what I'm interested in is, okay, how can I set up the coordinate from my personal angle? How can I do that? What is it determined? Is it determined by your device position or angle or whatever? What determine my coordinates? For the word general standard coordinate, I can understand. You just set it up. Okay, it doesn't matter. But how can you set up your own coordinates?
okay. So from my understanding that your coordinates from a device, when you're looking to a device, you always look at yourself as the 0, 0, 0, right?
Yeah. Mm-hmm.
And in the screen, you will see the virtual object you just placed it there. So that is a 2D image of it. And also you have the information of the way you are holding your cell phone or holding your camera. So what you get is actually the real world coordinates, which is x, y, z of the virtual object, if that makes sense. Because
So,
there are 3 relations. One is the pose of the camera. The other one is the 3D in the real world coordinates, and the other one is the image coordinates. Yeah. So these 3, as long as you get 2 of them, you should be able to get the other one.
so if I move, okay, for example, I move my head to the left or to the right, my coordinate change or not?
Yourself, your coordinate changes. Yes.
So it's always change. As long as I move, my coordinate change.
Yeah, and since you move your head, that means that the view, the pose you're holding is different, right? Because now your camera is facing the other way, so it all moves together. But the object you try to see is still the same, like and it's still where it is in the real world, right? So yeah,
my coordinate change. I understand the word coordinate never changes. It's like
yes.
I don't know, the standard ground truth or whatever. But
Yes.
whenever I move my coordinate change, right?
Yes.
That's my understanding. Okay.
Yes. Yes. Yes.
Okay. So the things they're trying to do is, okay. Okay. I mean, for RPTP, it's just like, if I move to that angle, then no. Okay. Okay. Yeah. Okay. Okay. Gotcha. Okay. Oh yeah. Please continue.
Okay. So with these, so RA and TA, they are known, and the RPTP, they are pretty much unknown at this point, right? Because you don't know how the host and the resolver and how the resolver looks at you. And here they say
So what does the RATA and RPTP stand for? What's the meaning of RATA? What's the meaning of RATA?
So the meaning of RTA is to try to get the to transform the world coordinate to the host device coordinate. And the world is like where the virtual object is. So you transform it and you get it in your host device. Because what we try to do is to get the relation between the world coordinate and the resolver, right? But we can't get that unless we get the information of the world coordinate and the host coordinate first. So this is like an inter step to do the final goal.
Okay, let me clarify my question. Okay, does it TA means the time?
Oh,
RA
okay.
means a rate or something,
Oh, sorry,
or RATA means a process,
Okay,
or
sorry.
means some physical meaning. Yeah.
Yeah. So R, it stands for the rotation matrix, and the T it stands for the translation matrix. So these two, you can just you can see it like these two combined is basically the pose transformation of it. And these two are usually combined in a matrix, and the combined matrix, they just represent the pose transformation.
But
So
for
when
the
I mentioned about
for
RATA, they are like together. Yeah.
T I can understand, but for RA, I still can. But anyway, yeah, T I can generally understand. You just input your original coordinates, you times the T matrix, you get the destination or receiver coordinates. But what is R? I still get confused. But anyway, yeah, you continue.
Okay. Yeah, so the RA is they just the rotation of the transformation. Yeah. Okay. So yeah. So what we try to do is to get the RP and TP here. So that leads to the one we mentioned about the multi-user PMP. So usually you get it from using the keyframe from the same thing, from the same device, right? But in multi-user, we can use the Alice's keyframes instead. So and we can compute the pose of Alice's device in Bob's coordinate system. What that does is that in that way, the pose you compute is actually the transformation of Bob, of the resolver, because now you're using Alice's keyframes, right? So that is how they draw the link between the host and the resolver, and that way they can get the transformation between those two coordinates. So now we have the transformation of from the host device coordinate to the resolver device coordinate. Then we can use this function. The third line, the first line is like they tell you like you can get it from the frame from the keyframes from host. Second one is that we implement the multi-user PMP to get the transformation between host and resolver. So the third one is just showing that the PB world, which is the coordinate of the resolver, is you can get it by implementing the one on the right. So you can see inside this is the RA and PA world TA. This is the inter step of the process. So it actually basically just means the device coordinates in here. So basically you just transform two times. Like first you transform from the world coordinate system to the device, to the host device coordinate system, and then you transform the host device coordinate system to the resolver world coordinate system. So that is how they do the coordinate alignment.
Okay, allow me to have a guess here. Okay.
Yeah.
So the RA is a kind of like transform matrix, right? The TA is kind of whatever is a composition or offset matrix. Is that something like that?
No, actually, RATA, they together is called the transformation.
I know, but just like AX plus B. Right?
Oh, yeah,
what's A's meaning? What's B's meaning? I want to understand that.
Yes.
So, but I want to further understand. Mathematically, I can understand, but so if you map TA to the real AR things, what is what's the meaning for that? It's like something, I don't know. You do the composition, is it or? So is there something unique in your host device? TP is something unique in your, I don't know, probably in your resolver device. So again, mathematical, I can understand, just like the matrix calculation, right? You do Y matrix equals to RA times X matrix plus TA matrix. I can understand that, but the RA part I can definitely understand, but for the TA part, what's that? To the physical, I mean, if you translate that to the physical things, what's that part for?
So the R is for rotation, and the TA is just for the translation of the process. So they
So when you do the rotation,
so they do. Yeah, R is the rotation matrix.
Yeah.
What we need, yeah. So what we need to know is just like these two together, they pretty much just form the transformation. But how those two individually affect the coordinates, they
okay.
not really give a clear explanation of that. Yeah.
Okay, let's start with a very simple example, right? For example, two-dimensional, right? If you want to move the 0.00 point to somewhere like 1, 2 point or 1, 1 point, you know, the new coordinate 1, 1 point will be the 0, 0 point. What kind of things you need to do? Then you do something like RA times original coordinate XY plus TA equals to the new coordinate XY, right?
Yes.
Then you need to give me what is RA, what is the TA. Okay, I think I can understand in general, but you know, that's the way, how can you explain this, right? You put things down to the simple stuff, right? Make people understand, right? So I mean, the purpose of presentation is not like to confuse the people, it's to make people to have a crystal understanding what you're talking about. You got the example I give you, right? 3D is difficult, you start with the 2D, or you start with 1D, one-dimensional, right? If you want to change our X from 0 point to Y point, what you need to do, right? Then extend to that 2D, what you need to do. Give a clear example, then people quickly catch up with you. Okay, yeah. Okay, I think I got that part then.
Okay.
Yeah, please continue, yeah.
Okay. All right, so that is what we mentioned about the coordinate alignment. So now we are up to the third, which is the concept is like resolver, they may move around and collect more information about the real world. So using the most recent keyframe will be bad if they're at a distant point. So what this one tries to do is to have an update of the new information collected from the resolver. So how they determine like what kind of information they want to get. So again, they choose the features that are near the virtual object. So that is how they determine the importance and the ones they will prioritize in updating. So how do they do that? So they use the feature geodistance, which is shown here. So like there are many points x, y, I, z, I, and minus the position, the correlation coordinates of the PB world. So basically, it's just trying to say that, let's say this is the object right here. So they try to get all those information, like the distance between them, and they determine a threshold, like they will send those, they will update those that are closer to it. So here is like if feature geo distance is less than a threshold and feature, then they return the new updated coordinates. So basically, this is the way they choose what to update, and how they choose it is by choosing those that are near to the virtual objects. Next one is the spatial inconsistency and drift estimation tool. What they try to do is that they place one or more markers into the real world, and they use the reference points for which to measure and compare the virtual object positions. So I'll give you a picture of how this works. So at the host, the virtual object is at this location, but in the resolver, the virtual object is at the other location. So this red line, it is the spatial inconsistency, right? So, but how do you know the spatial inconsistency? So what they try to do is that they set a marker. This is like a marker. So a marker that you know the distance between it and the host, and you also know the distance between the marker and the resolver. So in this one, A, B are known, A prime, B prime are also known. So with that, you can get the C and the C prime. And the spatial inconsistency is basically just C prime minus C prime, C minus C prime, and then you can compute the inconsistency. So this is the way to compute the spatial inconsistency by using the algorithms. So what we mentioned are
yeah.
yes.
For this one, why you want to calculate spatial inconsistency? If you get the red line, it helps you to quickly transport the coordinate or what? Why you want to get this information?
Okay, yeah. So what they do, they just simply, for the sake of just to know the spatial inconsistency, because the formal way of doing so is by using the human eye. And what does that human eye has some errors, and they can't handle all the differences. So this is just they just provide this tool to have a more convenient way to get the spatial inconsistency. And as for what does getting this inconsistency do to, like, what does getting this spatial inconsistency has anything to do to improve the other parts, they actually didn't say anything. So it's pretty much they just provide this kind of tool. So if later on, if you have other ways to other AR you try to compute, they provide this kind of way to do so, instead of just relying on manual with human eyes.
So it's kind of provides a calibration tool. Right?
Yeah, it's just a tool. It doesn't really improve the whole process or anything.
Okay. It provides a kind of objective calibration tool, instead of we purely rely on humans' eyes.
Yes. Yeah.
But how can you set up this? I mean, this reference point there in the real world. This A and B, A prime and B prime, or they're in the eyes of the host and the resolvers. You know what I mean? How can you set up this reference point? I mean, this A prime and B prime, they still rely on the the 0 point of the resolver. Still rely on human eyes. You take average to get them, or whatever. How can you get those A prime and B prime?
Okay, so A prime and B prime, they can get it with just the PNP method, right? Like you can use the 3D the image and the pose to do so. So like in Informa, we just talked about that you can get the resolvers pose and real-time coordinates. So these are known with the same concept of PNP method.
But that's still rely on people's eyes, right? So every time you move to newer position, you change, you have a PNP function or whatever, you change it to that position.
Yes.
But your coordinate setup is still rely on people's eyes, right? Why do you say this one is more objective, say more accurate than you directly use, the previous whatever multi-user PNP approach? Why do you think it's better? Or this one is a pre-trained or something? They have a lot of I don't know, empirical results. They take the average or whatever. I don't get the point of why this one is more accurate than the the previous one you present.
They pretty much just they didn't really mention about how they, like, I know what you talk about, like, you still need the human eyes, but they pretty much just assume these are just known factors of it.
I can understand their motivation. For example, when you do the AR, right? Because if you change to a new environment, I'm not sure it's because of coordinate things or something, but from real world experience, sometimes you find the screen is kind of shaking, right? Probably it's because of the coordinates transformation is not that good. So probably you need a reference things to calibrate that. I can understand the motivation, but I don't really catch the, I mean, their standard or their criteria here, or the whole design process. So, I mean, if you take an average, you have to mitigate this kind of oscillation, fluctuation, whatever. But if you still do this one-time thing, I really don't know. Besides, how can you measure every possible point, right? Because as long as your head move to an angle, move a little bit, your coordinate change, right? So what's the sample rate of the whole space? How many coordinates you need to create? Did you get my point over there? So I think the space will be very, very large. So what kind of an angle, people cannot distinguish? For example, the 1 degree or 2 degree, then people cannot distinguish the change. Is there any paper talking about something like this?
They didn't really mention how the human
I
eye.
don't mean this paper. I mean in general, in the literature.
No, they didn't provide any of those. They pretty much just assume that this is they just pretty much assume that this kind of way is better than the manual measurement.
But in this way, can you answer me that question? As long as I move my head a little bit, my coordinate change, okay? Let's say I'm in the same position, just moving my head. How many coordinates in total you can generate? The numerous one, right? What's the resolution? What's the units for X, Y, and Z?
So,
well, I know you just start this area, but I think that's the homework you need to do before the presentation, right? So, because this kind of a real world, more application kind of research is not like some other students, they present some theoretical research. There's this things and that things. But for this one, people is going to ask a very practical question. You need to be ready for that. I mean, the paper is very easy to understand, for sure. But there's some real world minor issues. Probably you need to think about that. For your own research, you need to pay attention to.
okay.
Okay, you just go ahead.
Okay. So now we will be at the implementation. So they talk about the devices they are using. Samsung Galaxy 7, smartphones running Android 8. The system, they use the C++ code with the Android NDK on top of this, a open source AR platform. And they use the spatial inconsistency tool is using the Python, using Python 3, using OpenCV and NumPy and their libraries. And now we'll talk about the scenarios they set up for this their experiment. So there are 3 scenarios. The first one is the small area. So pretty much the host and the resolver, they are mostly stationary, and they move within a one times one and one to one area. So this is the small area. scenario 2 in a large area and some initial position, then this initial position is the same. So what that means is that the host and the resolver, they start at the same place, facing the same direction. And then they started moving independently with a larger area. And the third one is the large area with different initial positions. So at scenario 3, those two are at different places. So they set up these 3 cases to examine the results of it. And the baseline is we have 4 of those. The first one is all, which means that the host that sends all the keyframes and associated point clouds. The second one is the sparse one, which it sends 5 keyframes from before and after creating a virtual object. The third one is sparse large. It sends keyframes from the host is within the frame 3 meters within the virtual object. And the AR core is just from a comparison, is a AR platform that is mentioned in other papers. So these are the 4 they are trying to compare together. First, we will see the latency for initial AR rendering. So this is the latency of virtual object appearance. So the 1, it means that it's in the scenario 1, 2 is scenario 2, 3 is scenario 3. And all those 4, save, communication, low result. So save is the time the host spends to adapt the data in preparation and transmission. So that is the time for host spending. And this one, the communication is the time spent to communication, to communicate the selected data to the resolver. And loading is the time the resolver spends to load the host data. And resolve is the time for resolver to move close to a virtual object and perform coordinate system alignment. So in this one, we can see the result in different scenarios. The first one we can see is in scenario 1, which is the small area. The small has the least latency compared to the others. And in scenario 2, that holds the same. But as long as we're at the time we're in scenario 3, which is the large area and different positions, this makes the large one smaller than had less latency than the sparse small. And also in this case, the all is the one with sending augmented, they have a lot less latency of virtual object appearance compared to the others. And now we're talking about scalability. This is talks about the communication time of those 3. So the first one is the.
Sorry. Could you go to previous page?
Yeah.
Previous one.
Okay. Oh, sorry. Yeah, this one.
Yeah. So this 1, 2, 3 means 3 scenarios, right?
Yes. Yes.
And for number 3, right? It takes almost like 13 seconds to finish the rendering and information transmission.
Yeah.
But could you go to previous page? For large scale, you send like the frame within 3 meters of a virtual object.
Yes. So
Okay,
they send the keyframes close.
Go to previous page. So your object moving speed is 2 meters per second.
Oh, they didn't say that you have to move in a.
So what's the 2 meters means?
It means that the range that those hosts and resolvers can move around. Like this is pretty much the space where you can just move.
The
So
initial, compared to the initial distance, they move within, I mean, the relative position, they move within 2 meters, right?
yes.
They don't talk about the speed.
No, they don't talk about the speed. They just talk about the space. The space. Yeah.
Well, that's the reason why they send a 3 meters frames.
Yes.
Yeah, okay. Yeah, I just try to figure out. I thought that they move like 2 meters per second. So altogether, 15 seconds, you can move like 30 meters.
No. This is just, it just tells us the area.
Okay.
Okay. And I'll continue. So this is the latency, and we talked about the scalability for as you can see, this is the number of resolvers. So as you can see, as the number of the scales, the one that transmits all keyframes will get much significant change in communication time, while as those two introduced in the paper, the SPAR, they have relatively they don't scale that much. So as you can see, the more resolvers, the better communication cost they will reduce. Now is the spatial inconsistency. Also, this is divided into 3 scenarios. So they didn't provide the last one in this picture. So in scenario 1, you can see that the small scenario, the sparse small has the least spatial inconsistency, and also in scenario 3 also has the same. So no matter which scenario you look into, the spar strategy here is always better than the one that sends all the keyframes. The next one is the updated AR rendering. So this is we talked about the feature geodistance of matched frames. So if we set the frames to be higher, then if it's like over 3 meters, then the spatial inconsistency will grow. And in the picture on the right, they talk about the spatial inconsistency, which if we have a feature geodistance filter here, we have a much less spatial inconsistency. Whereas if we don't do any of those, those inconsistencies going to be are going to be relatively larger. So to wrap up, what this paper is trying to say is that SPAR provide efficient communication strategies to lower latencies, and SPAR enables mobile devices, mobile areas to update their virtual objects as they move around. And the third one is they provide a tool to automatically quantify how much the virtual object's positions inevitably change in time and space. So this is the estimation tool to get the spatial inconsistency. And that is all. And are there any questions?